uh, is a single integrated circuit, as if all the functions in a motherboard were built together in one chip. So for an example, we can consider about the Raspberry Pi Broadcom BCM 2711 system on chip, or as well as the Apple A12 Bionic chip as well. So in terms of a definition of a system on chip, what we can say is a system on chip combines the required electronic components of various components into one single integrated chip. So that's it. So to give an idea about what is an intellectual property core, like in a system on chip, we see uh, there's a CPU, there's a GPU, there's a memory, there's a DSP module, connectivity module. All these modules are called IP cores. IP cores are like the reusable units of logical functionality within a system on chip, whereas there are multiple vendors in the world who build these IP cores, and in the design perspective, and these are combined into single chip at one place. So it's like the whole world is cooperating to build one single system on chip, and they can be like various issues due to that. We'll talk about that in the next slides. So then we talked about what is a network on chip, and a network on chip is widely used to interconnect these intellectual properties that I mentioned in a system on chip design, and it uses a packet-based communication approach. So there were like the complexities in system on chips due to the increasing number of cores, and network on chip has allowed the computer architects to fully utilize the computational power in a system on chip by facilitating low latency and high throughput as well. So this is an illustrative example about a system on chip uh, where the communication is happening through a network on chip. It connects all these IP cores inside a system on chip. So we talked about why do we need security in network on chip communication. So the one thing is like network on chip has all access to all system data, and the other thing is like it's span across the entire system on chip, and of course like network on chip elements are repetitive in a way that any modification can be easily replicated within a network on chip. So there were like challenges in network on chip security that we talked about. One is the conflicting requirements, because like while enabling communication between IP cores in a network on chip needs to satisfy a wide variety of requirements, including security, privacy, energy efficiency, domain specific requirements, and real-time constraints. So it is like difficult to satisfy conflicting requirements such as security and energy efficiency at the same time. So these are things that they have to uh, consider about, and due to these considerations and due to handling these requirements, there can be like uh, issues in terms of security as well. So for example, in an automotive network, when a potential security breach is detected, forcing all systems to check the malfunction is not an option, since the car is moving, and stopping it abruptly can lead to catastrophic consequences as well. So there needs to be an innovative solution to secure the network on chip communication with a lightweight security mechanism that is customized for every domain that this is used. So the second point that I had discussed was increase of complexity. So as I mentioned before, like due to the number of increase in the IP costs, there are like multiple vendors in different places in the world that are developing these designs, and most of these intellectual property vendors design these IPs as black boxes, whereas because the vendors do not want to reveal the design in order to maintain the competitive advantage in the market. So the last point is that there are like several types of network on chips we discussed on the second webinar. There are like optical network on chip, wireless network on chip, and electrical network on chip. And the security solutions for these network on chips are different, because uh, in one case that there are electrical wires, there are like hops from one place to another place. But in if you consider about the wireless network on chip, it it only has a single hop communication. So there are like plenty of different requirements and needs that we have to specifically identify in each set of these technologies, and that also cause challenges in network on chip security. So then we touched upon what are the security attacks that can happen, and we studied about these attacks uh, in a detailed manner last week. So I'll just touch on these attacks. So some of the most commonly known discussed vulnerabilities in terms of on-chip communication architecture include information leakage, denial of service, as well as data corruption. So the first attack that I can talk about is eavesdropping attack. So it's like listening to confidential information passed through a network on chip when other intellectual properties are communicating. So if there are two intellectual properties within a system on chip that are communicating, another one is listening and maybe like passing the information to somewhere else, maybe outside of the system on chip as well. So the second one is like spoofing or data integrity attack. So it is like intentional data corruption to cause erroneous behavior or system failure, whereas a spoofing is an impersonation type of an attack that disguises the communication from an untrusted IP as a trusted IP. So it's more likely there are, like as we have discussed last week, there are like A and C communicating, and there might be a person called B who is impersonating A and pretending to be A and communicating with C as well. So that's kind of a spoofing attack. So the third one is denial of service attack. So this attack opens the network resources in an attempt to cause performance degradation, real-time guarantee violation, and reduction of battery lifetime as well. So that's the denial of service attack. So the fourth one is the buffer overflow or the memory extraction attack. So it's about like gaining access to unauthorized privilege levels and memory locations. So we talked about how it can influence and affect the stack buffer in the system on chip as well in last week. So the final one is the side channel attack. So it mount attack by utilizing non-functional properties such as time, power, and electromagnetic radiation. So these were the types of attack that we have discussed, and today I'm gonna discuss about denial of service attack detection. So just let us just have an idea about denial of attack again, like because we are discussing about the detection mechanisms in denial of service attacks. So as I mentioned last week, like denial of service attack in a network is an attack that prevents legitimate users from accessing services and information. So the most important, maybe like most common example is an attacker is flooding the network with information, and when a user is trying to access a website, for an example, like the request is sent to the web server to view the page. So if the server has a certain bandwidth, like it can only serve a limited number of requests at a time. Let's say that there's a server called A and it can handle only 50 requests, and that means like it can handle only 50 users at one time, because if the number of users exceed 50, the site will not work as we expect because the bandwidth has exceeded. So if an attacker overloads the server with requests, it will not be able to process the user's legitimate requests, and this is called a denial of service attack. And in the context of network on chip, there are like several threat models as explored. So the threat models are like flooding, packet corruption, and traffic manipulation. Flooding means like a denial of service attack can happen from malicious intellectual property within a system on chip by manipulating the availability of on-chip resources by flooding the network on chip with packets. So the performance of the system on chip can heavily depend on few components. So for example, if there's a memory intensive application which is likely to send many requests to the memory controllers, as we discussed previously, so the routers connected to them will experience heavy traffic. So if there's a malicious IP, as mentioned here, the orange color one sends a tag targeting an IP which is connected to a memory controller, which is the blue one. It will increase the traffic rate, and the additional packets injected from the malicious IP to the victim IP cause congestion in routers and responses, uh, experiencing several delays. So that's about flooding. And then when it comes to packet corruption, it's about the continuous corruption of packets, continuous corruption of packets, and this can also lead to denial of service attacks, like maybe like tampering the fleets arriving in the input buffer of a router causing performance degradation. So that's one such example. And then the last one is like traffic flow manipulation. This is a threat model that whereas the packets are unfairly treated by the routers to cause denial of service attack. So if a malicious network on chip intellectual property picks a victim in intellectual property that is an important system on chip component, and it manipulates the packets to cause denial of service attack. So
Hello.
Yeah, we can hear you now.
Yeah.
hello.
Yeah, we can hear you now.
Yeah, what happened like previously?
I think there was a connection issue there.
So where did we drop?
At the beginning of the last slide, I think.
Yeah, I'll share my screen again. Just give me. Yeah.
Before that.
This one at the beginning.
Yeah.
Oh, okay. So this was also like I have discussed about this in the last webinar as well. So it's about today we are talking about detection of denial of service attacks, and in terms of denial of service attacks, they can be like 3 types of denial of service attacks that can happen in the network on chip environment. So for an example, if we talk about the denial of service attacks in the context of computer networks, one such occurrence is like if you consider a website, there's like the server in a website has a limited bandwidth, like it can only serve like 50 users at a time. But if an attacker overloads the server with requests, like it sends like maybe like 70 to 80 requests, the website won't be able to process the user's legitimate request there. So that's a denial of service attack. So in the computer network domain, in terms of like in the network on chip communication, there can be like 3 attacks, as I mentioned, like flooding, packet corruption, and traffic flow manipulation. Flooding is similar to what I explained, because like in denial of service attacks can happen from a malicious intellectual property manipulating the availability of on chip resources by flooding the network on chip with packets. So it causes like performance degradations of few components. So let us consider there's a memory extensive application there in the network on chip environments, and that needs to be on time, and it cannot violate deadlines. But if you consider there's an instance like in this image, as I mentioned, like in the orange color IP is a malicious IP, and it targets the blue color IP, which is a victim IP. So if the blue color IP is an IP which is connected to a memory controller, it it has to process many requests rather than the other IPs. But if the attacker is targeting it, there will be more than the number of there will be more packets than the number of packets that it can serve. So there'll be deadline violations there. So that's a flooding attack. The packet corruption uh, is like using the hardware trojans to tamper the fleets arriving in the input buffer uh, from the network. So there are like different packet corruption methods like quant Trojan, address Trojan, head hardware Trojan, tail hardware Trojan, and if you are interested, you can look into them as well. And then the last one is like the traffic flow manipulation. So it's like maybe like there's a IP in the system on chip that it requires to connect with three or four more other IPs which are near to them to pass messages. But if an attacker is targeting those set of IPs and then the one which needs to send messages will not be able to send the messages as it needed to, so the traffic is manipulated there. So that's called traffic manipulation. So in terms of like detecting a denial of service attack, there were like plenty of methods and explorations done previously. One such method is like traffic monitoring. It monitors the traffic within a network on chip, and then there was formal verification, like uh, uh, as in mathematics, they come up with like certain conditions, like if this condition is satisfied, there won't be an attack, or if this condition is not satisfied, there will be an attack. So there are like many formulas in denial of service attack detection in network on chip environment as well to detect whether there's an attack or not. So as well, they were like these denial of service attacks are very common in computer network security domain as well, and there are other methodologies in computer network domain to detect denial of service attacks. So that's about it. So one methodology to detect denial of service attack in the network on chip environment is to have a real-time lightweight denial of service attack detection technique for the network on chip based system on chip, because the lightweight mechanism is needed. Like this is implemented in embedded systems. It might be autonomous car, or maybe it can be implemented on a aeroplane. So it's like these uh, these vehicles or planes cannot be stopped to process this attack or the get rid of attack. So the method to detect should be lightweight, and it should be based on objects as well. So that's, as I mentioned in the beginning, if there's an attack in a car happens, we cannot stop the car at the exact moment, because we have to come up with some other innovative manner to tackle it. So in this method, the routers in the network on chip store statistically profile traffic behaviors and monitor packets in the network on chip to detect any violations in real time. And of course, like after this detection, this lightweight approach is able to localize the malicious source or maybe sources in real time once a denial of service attack is detected. So in terms of exploration of these attacks, so they can be like real-time explorations as well as in theoretical exploration. So in any case, what we have to do first is to have a threat model to find how we are going to tackle it. So in the previous work, there are like two main types of denial of service attacks and network on chip communication. So one, as I mentioned previously, one is the uh, flooding the network with users packets with a frequency of to waste the bandwidth, like it's called the synthetic traffic generation. And the other one is to have a specific application running in the system. So what we can do is like to have send useless packet from one IP to another IP to increase the traffic rate, or we can run a certain application within the setup. So these are the two threat models that we can consider. So then we need to have a communication model. Like in a communication model, what happens is like in here, like there are like two event traces. One is for the regular packets, so where there is not an attack, and the other one is to have an irregular packet set up, like because there's a compromised packet stream there. So the blue color one highlighted here is a normal scenario, and the red color highlighted ones are the attack scenario. So we can obviously see that in the attack scenario, there's the number of packets are going through within a certain period of time is higher than the number of packets in that time in a normal scenario. So one of the methods that has been considered to detect this attack is to have packet arrival curves and detection parameters. So this is done using packet arrival curve bound. Like this is done having a higher bound to detect what are the packets coming in a specific period of time. Let's say like uh, maybe in this particular time there'll be like 2 packets, and in the normal scenario this time there after like maybe like 5 seconds, maybe like there'll be like 20 packets. So this shows an overview of the security framework that we can consider. So in the first stage, like it illustrates the DOS action detection, and in the second stage, it represents about the localization as well. So, so in here, like we can see like the rightmost image shows the hop count. Hop count means I explained in maybe in the second webinar. So it's about the number of hops that an packet is take to go from the source to the destination. So if the hop count is increased in somewhere, that we can consider that that place is considered to be a malicious IP. So that's if I explain simply. So the threat localization can be done using the increase of count as well. So this is called an arrival curve bound. So this is one of the methods that we can use to detect a denial of service attack. So the y-axis shows the number of packets and the x-axis shows the time. So with the time, uh, if we consider one of the routers, there are like 16 routers in a network on chip mesh. If you consider 4x4 network on chip mesh. So if you consider one of the routers, what we can see is like in a normal scenario, the number of packets within some period of time, maybe like there will be one packet, 2 packets, 3 packets, 4 packets, and you can see in the normal scenario, which is the blue color one, the number of packets within a certain period of time will be less. And in an attack scenario, which is in the red line, you can see the number of packets might be increased. So depending on the application setups and what's running there can be like differences as well. So maybe the number of packets in normal scenario might increase or decrease. So this graph shows an upper bound that we can use to detect these uh, network denial of service attacks. So this is one of the methods that is currently used. So that's about finding whether there's an attack. So this is using upper bounds. And then, as I mentioned previously, we can find where this attack is happening by considering about the hop count. So this is a scenario of a normal operation and an attack operation. So in a normal operation, if you consider about the cycles, the hop count is around like 0, 1, 2, 3, 4, and the likelihood of having more hop counts for a certain specific number of hop count is less. Like it has a gradual increase, and there's a limited set of like values that we can have there. But in an attack scenario, let's say the hop count 4 has many cycles there, so we can easily detect there's a denial of service attack there. So there are like algorithms that we can use for these scenarios, because like if we consider about having an upper bound to detect a denial of service attack, what happens is like we need to have an entire packet stream to observe that, to get the higher bound at each time. But this is not practical. So in this example, what one of the methods to detect was taken using a leaky bucket algorithm. So which considers the packet arrivals and the history of the packet stream and gives a real-time solution using parameterized values. So you don't need to like instantly understand this algorithm. So but what you need to do is like to have an idea about like this an algorithm called a leaky bucket algorithm that we can use in these kind of scenarios. So when it comes to attack detection, as I mentioned previously, there are different topologies that you can come up with. Like there's mesh topology, there's ring topology, and there are like plenty of variations in mesh topology. And if we are to, if we want to like to show that this method or any other method can detect a denial of service attack, what we need to have is to show that it is applicable in different characteristics and different scenarios. So here it has been considered that uh, this method is effective in point-to-point topology, ring topology, mesh topology, in different scenarios of mesh topologies as well. So then this is an diagram which explains about the use of comparison of the attack localization time in different test cases. So uh, if we are detecting a denial of service attacks for one or more two test cases, there are like plenty of different application mappings which are running in the system on chips, right? Maybe we can test for synthetic traffics, which are like the ones that we create ourselves to check whether something is working. And now we can use different application mappings, as I mentioned previously. So different test cases should be used from different domains to check whether this is applicable or not. So in this scenario, like they have like done it for like 10 test cases and obviously found out that it works for all the test cases in all four topologies as well. In a really short period of time, this was detected maybe, yeah, within 1 to 2 microseconds, they were able to do it. So this is like using statistical bounds to detect denial of service attacks. So when we are detecting these using statistical bounds, there are like several limitations. So I'll talk about them. So the exploration in machine learning for detecting denial of service attacks in network on chip environment has like several motivations. So before like moving into machine learning and machine learning can do this thing, I just wanted to explain you that there are like other methods, mathematical methods we can use to detect denial of service attacks in network on chip. So why we need machine learning? There are like 4 points that I can address. The one is like the global trend of distributed design, manufacturing and testing of intellectual property of system on chips has raised serious concerns in this system on chip security and vulnerabilities. So I have mentioned it in the all three previous webinars that this is happening because of the complexity. And as I mentioned, in the statistical bounds and the other methodologies that were used are highly predictable network on chip traffic patterns, because like if we are to construct a linear statistical bound, we have to know about what is the type of test cases that will be there, because there can be plenty of variations within the setup if we have vastly different test cases, because the uh, upper bound might be vastly different from each other. So in these scenarios, the assumptions were like do not hold in like many realistic scenarios. So maybe like they might not include about task mitigation, task preemption, changing application characteristics due to various major input violations, and etc. So, and as well as I mentioned previously, machine learning was not used to detect a denial of service attack in the network on chip environment. So to detect anomalies using machine learning, so there are like two components that we have to focus on. One is the design time, and the other one is the runtime. So in the design time, what they use to do is like we emulate few normal and attack scenarios, and then we get the traffic data, and then we train the ML model. So just to make sure like this is a part of work that I have contributed, so I forgot to mention it. So this was the last semester project that I have done for the semester 5. So in the runtime, like in the design time, we train the model, and in the runtime, we gather network on chip traffic data for a specific time window. and then we send data to the security engine, which I'll explain later, and then we classify it normal or an attack scenario. So I just want to give you a high level overview of how to do in this. So then like this is the setup that I use for machine learning. So first we get the data, and then we extract what are the important data. So in machine learning, what we do is like we have numerical features, we have categorical features, and there are set of features that we can generate from the features that we extract from there as well. And as well, we might need new features as well. So these features might need to be label encoded, though we might need to like do a principal component analysis on these features, and then like we concatenate these features and standardize using like there are like several methods that we can use to standardize. Maybe like we can keep the outliers there as well, or maybe we can get rid of the outliers. So if you are into machine learning, you already you might understand what I have said. So but even though if you are new to machine learning, this image gives you a good understanding about what are the things that we have to consider about when we are using a machine learning algorithm. So there are like plenty of uh, uh, things that we have to consider about when using machine learning. So it's not about just training a model and testing it. So there are like uh, various things that we have to do to find what is the optimal model or how to use a model. So there are like different things that we have to consider, and this slide gives you an initial idea about how we can use machine learning for any of the projects that you are doing. So we can standardize the data, and then we can do feature correlation. It's about finding out whether the features that we are using have a similar set of characteristics. Like maybe like if we have A, B, C, D features, uh, what A and C are doing. If A and C are doing the same thing, we don't need A and C as features. We only need one of them. So in feature correlation, what we do is like we find out what are the redundant features in the set of features, and then we remove the redundant features. And there's a mathematical method called Bayesian optimization. So if you're familiar with machine learning models, there are various different parameters we have to feed into these machine learning models, and some of the parameters are intuitive because like from our experience we know that these are the set of parameters that we should use. But after like finding out the parameters using different test case scenarios and different trial and error scenarios, we find like maybe like if there are like 10 parameters that we have to consider, we might be able to find 5 to 10. But uh, to find the optimal parameters, there are like several methods that we can use. So one such method is called Bayesian optimization, which is a mathematical method. So we can use Bayesian optimization to find what is the best, what are the best optimal parameters that we can use. Then we can train the model, validate the model. Validation can be done in separate manners as well. So we can validate it by shuffling the data that we have. There are like techniques called cross validation, stratified cross validation, or we can use a train test split as well. So it depends on the scenario that we are using. So in machine learning, there are like classification, which is to classify if maybe binary classification, like if something is it is an attack or not. So that's what we do here. So there are like a class classification where we can consider this belong to class A, this belong to class B, this belong to class C. Or again, like this called regression, where we think about like determining about the price of a land in this area is this. So that's about regression. So we predict a value there. So this is classification. To be specific, this is binary classification because we want to know whether this is an attack or not. So then like we test the model, and then we can find what are the important features in this model as well. So after finding out the important features, we can remove the features that we do not need, because like having an overhead with unimportant features is not needed. And then like we can train the model again and test it and optimize and finally optimize it. So this is the threat model that I have used in detecting denial of service attack. So there's a node is same as the IP router. So there's a node with a malicious IP in an attack scenario, and in a normal scenario there's not. So in the normal scenario, what it does is like this communication between in this application mapping between router 0 and router 15, and in the attack scenario what happens is there's another addition of a router there. So the traffic rate will be increased because there's one more router which is running there. So that's simply the model, threat model that I have used. And this was done by using simulations to run what is happening inside a network on chip. So fortunately, I'll be able to run a simulation at the end of the presentation today. So just to give an idea about how we can run a simulation. Sorry. So I ran a simulation and I extracted the data from there. Like there are like different data that we can consider. And there are like instances that I made modifications and I got the data that I wanted. And after getting the data, what we can do is like we can fabricate features of our own. These are like 3 of the features that I fabricated. One is called traversal ID, one is called hop count, and the other one is called max packet count. So this is what we do. Like we get to know about what might be the possible set of features that might detect anomaly within a scenario in terms of communication. So these are the features that I thought that can be used. So some of them are intuitive and some of them are based on the previous work that people have done. So as you can remember in the previous previous explanation that I've done, I talked about using statistical bounds, and in using statistical bounds, they have considered hop count. So in my simulation, there was no way to find the hop count. So what I did is I included this hop count by using an algorithm of mine, and I found the hop count there. So that's based on the previous work, and the other things will be based on the explorations or the EDA. EDA means the exploratory data analysis. So that's a big part of machine learning as well. So if you are not familiar with that word, so you need to know about it as well. So these are the set of features that I generated, and then like we need to know if we get the features, how we can understand about these features, how relatable they are to what we are doing. So I relate them in terms of hop. Hop means going from one router to another router, and traversal means the entire communication of a packet, and then the characteristics that we can find in a packet as well. So we need to have an idea about what these features are and how we are using them. Have proper training and testing configurations when we are doing something. So because like in a network on chip, so it says my connection is unstable. Can you hear me? Hello.
Yes, we can hear you.
Yeah, great. So I thought that I might lose the connection again. Yeah, so this is about having training and testing configuration. So when having training and testing configuration, what we might consider is we need to cover the entire area that we are going to explore. So in this case, this is a network on chip environment, and this has a 4x4 mesh. So there are like 16 routers that we have to consider. So with each test case, we have to consider all 4 quadrants of the mesh. So there are like 4 quadrants here. So I had like 4 different test case scenarios for 4 quadrants initially, and I multiplied it to have 8 test training configurations, and 8 training configurations, and then like among these 8 training configurations, I can have testing configurations mapped to them. So this is done using like the previous threat model that I've explained. Like there are like two routers involved in the normal scenario, and there are like three routers involved in the attack scenario. Then we can map it to the test cases as well. So this is about training and testing configuration. And then, as I mentioned before, we have to do feature correlation to have an analysis about like whether we can go forward with a linear model or we need a non-linear model as well. So as you can see in this image, so there isn't a linear relationship between the features and the target variable, which is whether there's an attack or not. So here what is obvious is like maybe like we might not get good results from a linear model. So that's the observation, that's one of the observations here, and the other observations are we can see about whether the features are correlated as well. So if they are correlated, we can get rid of those features. So these are some of the last images of the feature correlation matrix that I had. So in the previous cases, like I had like around 30 features in the beginning. So then I figured out what are the features that we need, the correlated ones are removed, and this is more likely the final 20 features that I got. So after that, then what we do is like we run models, and from these models that we can use, and they can be divided into different parts. One is called linear models, and the other one is non-linear. In non-linear, we can divide into neural networks, gradient boosting, and tree algorithms, easy mathematical model, and then it's linear regression, which is mapping from X to Y, and we have then neural networks, which obviously we find them as black boxes, but I would like suggest you all to like just go deep into these models and see how they are implemented. Certainly when it comes to tree classification or gradient boosting, so you have an idea about what characteristics of these models are important to have a good in XGBoost classifier has the best accuracy, which is called 99.9. And before, the accuracy has to be attack detection has to be done in several set of examples. Like hello.
Yeah, you're breaking up.
Is that so? Just give me a moment, 1 minute.
Yeah, thank you.
Hello, how is it now?
Now it's good. It's clear.
Yeah, where did I break?
When you switch over to the last slide, just like from the beginning of this slide, DOS attack.
Okay, okay, sure. So in this slide, what I wanted to mention is like we need to have different configurations of attack detection methodology, experimental setups, so we can show that our model is performing in different scenarios. So here what I have done is like I have changed the number of malicious intellectual properties that are in the model, that are in the test case. So that's how it is happening. So then like we have to test it for different benchmarks as well. So I have considered like different benchmarks here. So they're like we have to run application in different setups. So one of the benchmark that I used is fast Fourier transformation application, and then we can consider like fast multiple metal radix, low upper bound symmetric Gaussian Seattle. So the idea that you have to get is like we need to show the model that we are using is robust and it uses machine learning. So the results shown here shows that the model is not particularly trained for a certain application mapping, and it's capable of detecting attacks with high accuracy on other benchmarks as well. So these are like the setups that we can use when it comes to detect those attacks. And in this scenario, like I was able to detect that we can use machine learning for denial of service attack detection. So this was what I wanted to cover today about how to detect denial of service attack using machine learning. And I'll show you how to uh, get this, like how to run a simulation setup of a network on chip communication. So in network on chip communication, we use a simulator called Gem5. So I'll show it. Just give me a moment. Yeah, I just stopped screen sharing, so there's nothing to worry. Yeah, so can you see my screen? So we use an simulator called Gem5. So if you're not familiar with, there's a documentation there. We can install the simulator without any problem, and there are like certain set of dependencies that we need. And if we are able to have those dependencies without any issue, we can have this installation done. Then in Gem5, the easiest thing to start is to do garnet synthetic traffic. So this is about maybe doing traffic generation from one place to another place in a network on chip environment. So I think if you're interested in this set of this field, you can have an idea about how to have different models run in Gem5. So this is a case like this is in this example, this shows that we can run a synthetic traffic generation. It means that this is not an application mapping, but we are just sending packets from somewhere to another place. So in here there are like 16. This is a 4x4 mesh of a network on chip environment, and there are like 100 cycles that we are running. So you just don't have to explicitly understand what I'm saying, but this is a simple explanation about how we can simulate this in a Gem5 setup. So I'll run it. So here what I'm going to do is like I'm having a 4x4 network on chip setup. So there are like 16 directories and 16 CPUs, and I'm using two senders here. So I'm going to send from router 1 and router 2 to router 14 and router 15 specifically. So router 1 is going to send into router 14 and router 2 is sending to router 15. So when I run this command, what happens is like this is a warning because due to the using in floating point. So this is actually how a simulation is running. So if I explain from somewhere around here. So this explains how the communication is happening in network on chip environment. So the first thing that happens is that when a packet is injected, it connects with the network interface, and after connects with the network interface, here the connection to the network interface, and then the router wakes up at the network interface, and then there's a switch allocator which directs the router to the packets to where it needs to go, the destination. So there are like what is the destination network interface, what is the destination router, and these set of information are there. So this is a simulation, and these are what we get in as the simulation traces. So if you want to get an understanding more about what we are doing here, so we can change like the debug flag that we are using. So here we are using the debug flag as Ruby network, and we can change the use of debug flag as using network to garner synthetic traffic. So I changed the debug flag. So now the set of traces that we are getting are different from the one that we got previously. So here we get like what from what sender to what destination we are sending. So if we consider this example, we are sending from router 1 to router 14, and this is the 25th packet that we are sending, and the address of the packet is 380. And then again, like we are sending from router 2 to router 15, and it's the 25th packet of that router as well. And the completion of injection is done at this point of time. So this is not actually the time, so this is the tick rate. So there are like a certain set of wordings and the wordings that we are used in this environment. I just wanted to let you know that this is how we are going to do it. So this is, yeah, this is how you are using gem5. So if you are interested in this domain, you can you can install this software. So you can either use Windows and then install Ubuntu on top of Windows and use it, or maybe if you are having Ubuntu, you will be able to use it without an issue. So if you're interested, you can look into this simulation software. So that's it from my end. So I think like you got an idea. I just wanted to give you an idea about how you can detect a denial of service attack in the environment of a network on chip. So I did it on a very high level that how you are able to do it. So if you have any questions, please let me know. Thank you very much.
So if you have any questions, you can ask now. Okay, since nobody has questions, let's end the meeting. So since we have reached the end of the webinar series on network on chip security, I would like to thank Chamika for conducting 4 amazing sessions on this topic and all the participants who joined with us throughout all these sessions. So I hope all of you learned something new and have a good idea on this topic. And later I will post a link to the feedback form. So please give us your feedbacks. And with that, I'll end the session. Thank you. Hi, so the link for the feedback form is posted. So please give us your feedback, and thank you and good night.